Trent's such an engaging speaker that I wanted to ask him to come give a talk for Champaign County Audubon. So Dr. Trent Ford has been the Illinois State Climatologist since 2019, and he and his team provide information online through traditional and social media and by speaking to interested groups across the state. So if you have a group that you think he would be great to talk to, then send him a message. And in addition to his role in education and climate outreach, he also conducts research on the climate system and extreme climate events like drought and heat waves, and monitors current conditions and studies climate change. So he's a native of Roanoke, Illinois. Ford earned a bachelor's in geography from Illinois State University before completing his master's and PhD at Texas A&M. And before joining the Illinois State Water Survey, he was an assistant professor in the Department of Geography and Environmental Resources at Southern Illinois University in Carbondale. And so today he's going to give us a presentation about what I call the once and future climate of Illinois. So thank you very much for coming. So if you want to try to share your screen here.
Yep. Okay. Can everybody see it all right?
Yes.
Okay, good deal. I'm just gonna, Zoom says, oh, we'll put these giant helpful controls on top of your screen. So I'm gonna disable those real quick.
Yes, I agree.
I can see.
Okay.
Perfect. All right. So thank you, for letting me come speak today or tonight. So I will admit I threw in some bird information as much as I could. To give you an idea here, since taking over the position a little over a year ago, I've probably given 40, close to 50 talks. Most were in person. Now we're shifting towards virtual. And a lot of the talks are like this, where it's an interested group of folks, most of which are not climate scientists, sometimes none of which are climate scientists, but they're interested in some piece of climate. And often it's climate change, understanding how that affects what they're interested in. And so what I like to do is customize things just enough to try to meet the group halfway where they are. And so although I love birds, I must say I'm not an ornithologist. And so I'm going to focus a lot on climate, and then I'll throw in some bird specific information that you've probably already read before. But as Sarah mentioned, so I'm originally from Roanoke, Illinois, and I've kind of touched all parts of the state throughout my life, being at Southern Illinois and ISU, and now here in Champaign. Professionally, as a researcher, a lot of my research deals with land and atmosphere interactions in the climate system, and especially using the information we can get from the land surface, and specifically soil moisture, for better information, understanding, prediction of drought and extreme heat. And so that's really where I come from professionally, although in the state climatologist role, it's really focusing on all aspects of climate ongoings in the state. Okay, so I'm going to first start off by giving a brief overview of the climate system and Illinois' climate in general, and very generally before I start getting into climate change. So when I talk about the climate system, a lot of times I like to include this slide because a lot of times people think about it's just the atmosphere. But in fact, the climate system is the entire critical zone, from atmosphere to biosphere to lithosphere and the hydrosphere and the cryosphere, all the spheres kind of put together. The climate system really encompasses all of those. And so when we talk about climate change may first and foremost be measured by changes in atmospheric types of quantities, temperature, precipitation, humidity. But in fact, because the entire climate system affects essentially everything we do as humans, the impacts are far-reaching. And as you can see, there's many arrows in this very simplistic schematic that are not just one-way arrows, they're two-way arrows. So there's interactions, which means that impacts are nonlinear. They interact, there's feedbacks, and they can magnify or dampen different impacts. And so overall, what that means is that climate change, although it's caused by simply an increase in global average temperatures, the impacts are diverse and far-reaching. Okay, so we go to the Earth's energy budget, and this is kind of where we start when we want to start to understand global warming. So virtually all the energy that creates and causes our weather here on Earth comes from the sun. And that shortwave solar radiation comes to the atmosphere. It's absorbed or reflected by the Earth. That can be in the atmosphere or the land. What's absorbed can then be re-radiated by the Earth as a different type of energy, terrestrial or what we feel is heat energy. In general, these quantities should balance. So in this very highly simplified schematic, we have 100% of that energy coming from the sun here. 30% of it roughly, of course it varies where you are, but roughly 30% is scattered or reflected back into space. The rest of it is does something here on Earth, and then the remaining 70% is radiated. So in general, we have this Earth energy, I call it a budget here, but we consider an energy balance. All right. And we have the kind of celestial scale interactions as well. So Earth is a sphere. Hopefully it's no surprise to anybody. And it's tilted. Right now, it's about a 23.5-degree tilt. And so what that means is that at different times in our calendar year or in our celestial year, we will receive different amounts of energy because of their solar angle and to a lesser extent, the distance from the sun. So what this means overall is when we think about it over a longer time scale, multiple years or multiple decades, we get this. We get the fact that because of the sun and earth geometry, in general, around the equator, we have a net energy surplus, which means that over a long period of time, we gain more energy in the earth system than what we lose. We think about energy can be thought of as somewhat simple terms that if you gain energy, your temperature which is just a measure of the energies essentially of your molecules, will increase. And so overall, this area here around the equator to roughly 30 degrees north and south latitude, that gains energy overall. Once we get north of 30 north or south of 30 south, we see a net energy deficit. So where we are in Champaign, close to 40 degrees north latitude, we overall have a net energy deficit. In general, over years, decades, centuries, millennia, we lose more energy than we gain. And so this energy imbalance that's inherent in the earth or on the earth, it goes to drive our atmospheric circulation, our ocean circulation, to try to balance out this imbalance of energy. And in the process of the Earth system trying to balance that imbalance of energy, weather is generated. And so I would pose to my questions to my students at SIU the question of, if Earth was flat, let's say it was a cube instead of a sphere, and one side of the cube were to get the same amount of energy all the time, would we have weather? Because there would be really no reason that there'd be no energy imbalance, therefore no reason for air and ocean and water to mix to try to mix up that energy. It was kind of a weird theoretical exercise for them to try to understand energy balance. And so what we get then when we focus in on the US are different climate regions, different climate classifications. This is a map of the Köppen-Geiger classification, which maybe some of you have heard of the Köppen classification of climates. This is just one step up from that to take it to more classifications, get down to a finer scale. And so, over a long period of time, Illinois is really split between two climates overall. It's split in this case between what is known as a desert, fully humid, hot summer, snow, fully humid, hot summer, or a warm, temperate, fully humid, hot summer. And so basically those two classifications are really differentiated, those two climates, the difference between the dark purple here and the green are really differentiated by cold season weather. So the differences in temperature, the differences in overall seasonal weather between northern Illinois and southern Illinois tend to be largest in the cold season, less so in the warm season. And so overall, what that means is that Illinois tends to have cool to cold winters that tend to be snowy, particularly in northern Illinois, humid all year round, water energy limited, meaning there's surplus water pretty much all year round, and our summers tend to be hot because of that continental climate. Now, what that means for us here in central Illinois, I'm going to skip that slide because I want to come back to it. Here in central Illinois, this is pretty much what we get. This is an example of a climograph that I've broken out. On the left-hand side is our monthly temperature, maximum temperature, minimum temperature, and average temperature. And then the right-hand side, precipitation. So overall, this is no surprise to anybody who spent a full year, at least one full year in central Illinois, that we have quite a large temperature, seasonal temperature difference between winter and summer, not quite as a large continentality as what we were talking about earlier with eastern Montana dropping 80 degrees in a matter of hours. But overall, we do have hot summers and relatively cold winters. Precipitation, we do have a wetter season, although we don't have a defined wet or dry season, but our wetter season overall tends to be late spring into early summer. So the months of May, June, and July, and to a lesser extent August, tend to be our wetter months. January, February, our colder months also tend to be our drier months. That has a lot to do with the amount of water vapor in the atmosphere, the kind of systems that can bring that type of precipitation. So the slide that I split, when we think about, the factors that control our continental climate here in Illinois, first and foremost, of course, is the sun. We also have passing weather systems. We have these transient weather systems, the low pressure systems, the mesoscale convective systems that bring us our not only the precipitation, which we often associate with these weather systems, but also a change in air mass. So we can get cold front passages that not only bring us a different air mass as far as temperature, but also humidity. It's funny, we don't often think of topography affecting climate here in Illinois. In central Illinois, on a large scale, it really doesn't have much of an effect because on a large scale, we don't have a whole lot of topography. But when we get to some of the finer resolution down in southern Illinois and parts of the Shawnee, we do actually see a significant difference in precipitation over the course of a year because of some pretty large changes in topography, where we can get a change of 500, 600, 700 feet in a relatively short distance. Urban areas definitely have an influence on climate. Of course, we can hear about a lot of times about the urban heat island in Chicago, but there was a student actually who I helped out who measured an urban heat island in Carbondale. And to give you an idea, if you've never been to Carbondale, it's about 25,000, 30,000 people, so relatively small city. And even just the change in land cover and the kind of hustle and bustle of the urban core in a small place like Carbondale can still have that urban heat island effect. And then, of course, as we get close to the northeast corner of the state, we have Lake Michigan, which definitely has an influence there along the lakeshore. So overall, we have a climate here that can be overall summarized as having large temperature changes, quite a lot of seasonality, but overall wet all year round. It's when we have a drought or a dry spell, it's part of our climatology, but it's not something that happens frequently. Now we can kind of shift into climate change, what we've observed over the last 100 to 150 years. So I bring you back here to this energy budget schematic here. And I want to focus here on this thing, the greenhouse effect. So certain gases in the atmosphere, they permit the short wave, the solar radiation to come into the atmosphere. And then, of course, the Earth does with it what it will. It re-radiates that energy as terrestrial radiation. But the same gases that are essentially transparent to the shortwave radiation absorb or trap the outgoing long-wave radiation. And so what that means is that the higher the concentration of these gases are, the more the energy is going to be imbalanced. The more of the shortwave radiation can come in, but the more of that long-wave radiation that gets stuck here. And of course, the more energy that's kept here on Earth, the higher Earth's temperature is. So these gases, because we can think about it in somewhat of an analogous way as a greenhouse effect. We don't want to take that analogy too far, or that metaphor too far, but essentially same kind of processes in a greenhouse. These gases get the nickname of greenhouse gases. Those namely the ones that are most important throughout Earth's history for regulating temperature are carbon dioxide, methane, CH4, and water vapor, gas form of water. Now, interestingly, all three of these gases are variable gases, which means their concentration in the atmosphere varies significantly in time, both due to natural causes and to anthropogenic or human causes, okay? And that's really important. If we were to see nitrogen, for example, as a greenhouse gas, nitrogen's concentration is relatively stable even on longer time scales. But carbon dioxide, methane, water vapor, it's a lot more dynamic. So their concentrations can change even in a relatively short period of time, as I'll demonstrate in just a little bit. The forcing of temperature, right? The change in energy that comes along with changing concentrations of carbon dioxide in particular, that change in temperature is caused from that. That's called radiative forcing. And so when we have an increase in temperature, an increase in energy imbalance because of carbon dioxide, we refer to that as a radiative forcing because it initially comes from a change in the amount of radiation that's kept here on Earth. And so, you know, what we've seen over the last 50 to 60 years since we've been taking direct observations of carbon dioxide concentrations on Mauna Loa in Hawaii, which is what this record here on the right-hand side shows, is we've seen a pretty precipitous increase in global carbon dioxide concentrations. I haven't updated my number. I don't think the number for October as a whole has been released yet, but September 2020, we're at 411 parts per million. And you know, to give you an idea, when we started this observation back in the 1950s, we were at about 311 parts per million. So we've increased by about 100 parts per million over the last 50 or so years. I should note here that 411 parts per million because that does become important in just a little bit here. So, you know, that's over the last 50 to 60 years of direct observations, but we can go back in time even farther. So what I'm showing you here, the red line is really what I want you to focus on the top. The black line is a reconstruction, so it's less important here. What the red line is showing are direct observations of carbon dioxide concentrations from the Dome Sea ice core in Antarctica. And those observations going back 800,000 years before the present. So the way you can read this graph is that we go 800,000 years before the present, on the left-hand side, all the way to the present time on the right-hand side. And the nice thing about ice cores as proxies for paleo or past climate is that when the ice forms, of course, ice on an ice sheet like in Antarctica, it forms from snow falling one season and then the next season snow falling, and over again over long time periods that snow gets compacted. And as it gets compacted, it first turns into something called firn and then later into ice. When that firn initially forms, there are air bubbles that are trapped. The air between the snowflakes is trapped within that firn and then later on in the ice as ice bubble, or excuse me, as air bubbles. And so when you take that ice core out, those air bubbles that had formed at the time that the ice formed, the air inside those air bubbles contain gases from the atmosphere at the time the ice formed, in some cases 800, 500, 600, 700,000 years before the present. And so the great thing about ice cores is that when they're extracted, we can actually directly measure atmospheric chemistry that many years before the present, which is something that is unique to paleoclimate proxies. Usually with a proxy like coral or tree rings, we have to statistically relate something like tree ring width to something like precipitation or temperature. In this case, we can take direct observations. So I digress here. With that being said, these are direct observations of atmospheric carbon dioxide concentrations going way back. So you can see ups and downs, wiggles and squiggles in the line. We do see quite a lot of naturally caused variability in carbon dioxide concentrations. However, what you don't see is carbon dioxide concentrations over the last 800,000 years ever exceeding about 300 parts per million. Now, to go back, to remind you, we are currently at 411 parts per million, and we've increased from about 311 parts per million to 411 parts per million over a matter of 60 years. Now, it looks like a lot of these increases and decreases happen rather quickly in this long time series, but if you think about it, the resolution of any time step here is 10,000 years. So what we've seen over the last 50 to 60 years is an unprecedented increase in carbon dioxide concentrations at a very, very fast rate. And so what we're dealing with right now in the atmosphere is carbon dioxide at a level that humans have really never experienced. And so scientists have done a fairly good job at attributing the large increase in carbon dioxide concentration over the last 100 years or so to anthropogenic or human-induced activity. So the vast majority of that increase in carbon dioxide concentrations and the radiative forcing that comes from that, the change in temperature, are from these anthropogenic activities, mainly through energy creation through burning of fossil fuels. And so the result, as we know, is the result of that increase in carbon dioxide concentrations is an increase in global average temperature. What I'm showing here, these moving lines, are that change in global average temperature from the late 1800s to the present from 5 different data sets. And so you can see they can match up quite well. So what this is showing is that overall, because of this increase in carbon dioxide concentrations that changes the energy balance, keeps more energy here on Earth, we see an increase in global average temperatures. This phenomenon that I'm showing here is what global warming is referring to. A lot of times global warming, climate change, they're used synonymously, but in fact, they're not the same thing. Global warming is simply the increase in global average temperatures that we've seen consistently over the last 100 to 120 years. And global warming is what causes climate change. So real quick, before I keep going, what you can see here is that globally, our global average temperature has increased by about 1 degree Celsius over the last 150 years, which really isn't a whole lot when you think about daily climate or daily temperature variability just outside your window. However, because that 1 degree Celsius represents a tremendous amount of energy because it's increasing the global average temperature, what that means is that amount of energy, that global warming, has resulted in very large impacts or very large changes in climate in different places. So different regions, climates have changed in a different way. And so that's just one point I wanted to make, is that even though the absolute temperature change itself seems like it's very small, because the global average temperature, it really does have large impacts as far as climate change is concerned. So from here on, what I'm going to do is talk about climate change impacts specifically to Illinois. I could spend 8 to 10 more hours talking about global climate change impacts, and I will not do that. For all of our sanity, but I really want to focus here on Illinois. First, I'm going to talk about temperature, and these are really past, climate change impacts that we've seen so far, or changes in climate that we've seen so far, because it's important to understand climate change is not just a future phenomenon; it's a present phenomenon as well. Okay, so here what we have are these maps are showing the seasonal change or trend in temperature for each of our 4 seasons here in Illinois. These are showing the temperature trends in degrees Fahrenheit between 1895 and 2019. That's where our records tend to cover that period of time. So statewide, annual average temperatures increased by about 1/10 of a degree Fahrenheit per decade over that 120, 125 year time period. What you can see, if we break that down by season, winter and spring are warming at a much larger rate than our summer and fall as far as average temperature is concerned. You can actually see some places in southern Illinois, Massac, Gallatin, Hardin counties, they're actually exhibiting a cooling trend over that time period in the summer and to a lesser extent in the fall. I'll talk about why that is in just a little bit here. But overall, we see warming, and that warming tending to come disproportionately in our winter and spring season, and especially in the winter season. And when we break that down by maximum and minimum temperature, we begin to see different explanations for that. So for winter and spring, and to a lesser extent fall, maximum temperature and minimum temperature are changing. So our daily maximum temperature and our daily minimum temperature are increasing by roughly the same magnitude. But in summer, what we can see is that the maximum summer temperature has decreased slightly, and in reality, it's not significant. So it hasn't changed over the last 120 years, but our minimum summer temperature has increased by a large rate. A lot of this is due to changes in humidity. So in the summertime, as we increase those temperatures, the saturation vapor pressure, the amount of water vapor that the air can contain, that atmosphere contains, that increases. And because we're in Illinois and most of the time we have abundant water supply, added to the amount of water that is blown in from the Gulf of Mexico, as the temperature increases and as the amount of water vapor that air can hold increases, the amount of water vapor actually increases. If you think about changes in humidity, as humidity increases, it also makes it more likely we're going to have cloudy conditions. And if you think about a summer in the middle of summer, a cloudy summer day generally depresses maximum temperature. A cloudy summer night generally increases minimum temperature. And so that's partly what we're seeing here, is that we're seeing that difference between summer maximum and summer minimum temperatures. What the overall change the warming has done, one impact is it's also led to a pretty large increase in evaporative demand, or how much evaporation or water vapor the atmosphere can take in at a certain time. And of course, again, as we increase the temperature of that air, the amount of evaporation that can occur also increases. And so what I'm showing here on the right-hand side are observations, trends and observations from our Illinois Climate Network station in East Peoria on the campus of ICC. And this is showing an increase in mean temperature over the course of the year between 1990 and 2019 here in East Peoria. And corresponding to that with the red line is reference evapotranspiration, essentially a measure of the potential for evaporation from the land surface to the atmosphere. We can see that's increasing. Actually, when we look at it monthly, the largest increases, the largest change statewide in evaporation, or evaporative demand at least, are in the late summer to early fall, the latter half of August to the earlier half of September. And I'll come back to this when we start talking about drought a little bit, but this is really important to say that our evaporative demand, or the amount of evaporation that atmosphere can take in, has increased as our temperatures have. However, precipitation has increased even more. And so what we're finding is, and this is one reason why humidity's increased so much, is that as evaporative demand increases, evaporation also increases to meet that demand, because we have enough water at the surface until we don't. And that's an important point when we start talking about drought. So the thing about climate change impacts related to temperature, health impacts are extremely important. So what I'm showing here on the right-hand side are tick species collected in 2018 from the U of I Vet Med. And what this is showing is just the number of tick species and then differentiated by different tick species that were found in Illinois in 2018. So for example, Heartland disease, which is spread by the Lone Star tick, was confirmed in Kankakee and Williamson counties for the first time last year. What we're seeing is that overall, especially tied to warming in the winter time, we're seeing that the overwintering of these pests, or of these vectors that can spread certain diseases like ticks or mosquitoes, they're increasing in incidence because of that winter warming, or tied to that winter warming. So what we're seeing is a higher prevalence of, for example, Lyme disease in West Nile and Northeast Illinois. That's not only related to winter warming, but also these short-term dry spells in the summertime like we had this year. We also see an expansion of geographic range of things like the Gulf Coast tick, which is shown here in the purple in St. Clair County, as well as found here in Champaign County last year. I will say that our understanding of vector-borne disease impacts on ecology health, including the health of fauna that aren't humans, are lacking those of human health. And that especially goes for, or that is also true for livestock. So when I talk to farmers and producers a lot, you know, the spread of vector-borne disease a lot of times, and that increase of that tied to climate change, is often expressed as human health impacts, but it has an impact on our ecology and our livestock as well. And so that is an important impact that we are seeing the spread of these vectors, and an increase in the prevalence of the disease that they can spread. Okay, so switching gears a little bit to precipitation in Illinois and the change in precipitation. So overall, as I'm showing annual precipitation here statewide from 1895 to 2019, overall, Illinois' annual total precipitation has increased by about ½ an inch per decade over that 125-year time period. And when we break it down by season, we see differences in season. Summer wetting trend, that increase in precipitation trend, is about 2 to 4 times larger than that in other seasons. The increase in precipitation, especially in spring and summer, are largest in southern Illinois relative to central and northern Illinois. That is important because I'm going to contrast what we've seen over the last 125 years with what climate projections or models are projecting for the remainder of this century as well. But overall, Illinois has gotten wetter. Every season has gotten wetter. It's amazing. I don't have my county maps in this presentation, but if you look at county map trends, the trends may not be statistically significant in every single county, but they're of the same sign. All 102 counties show a wetting trend over the last 125 years in every single season. So that signal is definitely robust. Along with a change in overall total precipitation, we also see an increase in precipitation intensity and the frequency of very heavy precipitation events. To give an idea here, for example, is just, I like throwing out this statistic because it's absolutely incredible. This May was the wettest on record at Chicago O'Hare, and that broke the previous record, which was set in 2019, which broke the previous record from that, which was set in 2018. So this year represented the third consecutive year that we broke the wettest May record at Chicago O'Hare. I had a friend of mine, Justin Schoaf at SIU Carbondale, calculate, because he's a big statistics guy even more than I am. So he was calculating the probability of doing that. If we consider a binary of yes, we broke the record this year, no, we didn't. And the probability of doing that was just astronomical. And so this is what we're seeing, is we're seeing an increase in not only total precipitation, but precipitation intensity, the increase in the frequency of those very intense events as well. What I'm showing you here on the right-hand side is from our Eastern Climate Division here. It's a change in the 1-day and 5-day total precipitation based off of the recurrence interval estimates from rainfall intensity estimates based on 1989 data and 2019 data. What we see overall is that over the last 30 years, we've seen our 1-year, 10-year, and 100-year precipitation totals increase by quite a lot. So what that means is that what we would have classified as a 100-year precipitation event, you may have heard of the 100-year flooding event, right? 100-year flooding event has that 1% chance of happening any given year. What we found is that over the last 30 years, our 100-year precipitation event for a 24-hour period has increased by over 1 inch here in the Eastern Climate Division, which means we're seeing more frequent exceedance of those really intense precipitation events. Last year when I was giving, or earlier this year when I was giving a talk, I used a few examples from 2019. I was going to do that for these talks this year, but hey, 2020, even though it's been a drought year in Central Illinois, has actually been has given me a number of pretty intense rainfall events as well to talk about. So for example, in Chicago, one of the events that made it such a wet May was that they received about 8 inches of rain in a 4-day period. Now, based on the 1989 estimates in the original Bulletin 70 from the Water Survey, that was a 50-year event, meaning it had a 2% chance of observing about 8 inches of rain in a 4-day period at O'Hare any given year. Based on the new 2019 estimates, that's now down to a 25-year event, which means the frequency, or I should say the probability of this type of event has doubled over that time period. And that gives you an idea for how much more frequently we're seeing those very intense rainfall events and the impacts that can come from that. Flooding in agricultural fields, flooding in this case from May along I-80 and interstates. The third picture there with that car flooded is from Quincy earlier this year. So we see really large impacts both in urban and rural areas in developed agricultural and natural ecosystems from that flooding. And so I don't want to get too bogged down with these equations here, but this is just to demonstrate that as we see precipitation intensity increase, it does a couple of things. First and foremost, it increases runoff. So we're not netting as much water in our soil because we're seeing more of that water going to runoff. So as that precipitation intensity increases, what it means is that that water is running off into our streams, overland flow, and then into our streams, backing up those streams, and of course, increasing the risk of both flooding, riverine flooding, and flash flooding as well. That runoff can also create economic and environmental issues. So this image here, which is from a field in Illinois, we see that topsoil running off as well as nutrients, likely nutrients that are running off from that agricultural field as well. That creates an economic issue. Of course, if you're a farmer, you're pretty much your entire livelihood is in that soil. But also it creates an environmental issue. As we see the runoff of those nutrients, it increases the frequency of harmful algal blooms and hypoxia zones like what we're seeing in the Gulf of Mexico. At the same time, on the flip side, if we have more runoff from those intense precipitation events, what it means is that soil is not netting as much water. And so if we have a really intense precipitation event and then a prolonged dry spell following, the soil is going to hang on, is going to net less water from that very intense precipitation event, and therefore the ecosystem is going to be more prone or vulnerable to drought later on. We saw that this year in a very intense way in the Peoria area. The Peoria airport actually measured right at 50% of their entire summer precipitation in one day this year. So if you think about when you look at summer statistics for rainfall in Peoria, the summer looks like it's right about normal. But in fact, what it was a prolonged dry spell that turned into drought, followed by really intense flooding because of a very intense precipitation event, followed by more prolonged drought. And so statistically, it looks good, but when you think about the ecosystem and agricultural effects of that type of hydrology, it's not. It's definitely, it tells a different story. And so that's what we're seeing with that increased intensity, the frequency of those intense rainfall events. So a seamless segue here to talk a little bit about drought. So we have observed changes or decreases in the overall frequency of drought. And I should say the complexity of drought does complicate its measure and its projection into the future. But overall, what we're seeing is that these large multi-year droughts that are part of Illinois' climate, we think about the 1930s, the 1950s, to a lesser extent, the late 1960s, those large multi-year droughts are just not happening as frequently, or they haven't happened over the last 30 years. What I'm showing here on the bottom left, that is the annual Palmer Drought Severity Index, just an index that measures, actually represents soil moisture drought. And I applied a 30-year smoothing window to this. And basically what you can see is that on the right-hand side, in the late 70s, early 80s, we see this switch to a very wet time period. So the last 30 years here in Illinois are wetter than any other 30-year period on record going back to the late 1800s. If we go very far back to the mid to early 1800s, we do see a wet period that matches in intensity what we have today. But overall, we haven't seen really since the droughts of the 1960s, those prolonged multi-year drought periods. Now we think about 1988, 2012, those were drought years, but those droughts lasted fewer than the 18 months that are necessary to really have an impact on water availability for humans and ecosystems. And so those multi-year droughts, because we're seeing an increase in precipitation, they're just frankly not happening as frequently. However, what we are seeing is this change to more frequent short-term but severe droughts. Some folks talk about flash drought. I don't really want to get into flash drought here because it's quite a kind of a lengthy issue. But essentially, what we're seeing here in Illinois is an increase in variability of short-term precipitation extremes. Like I talked about in Peoria, where we get 50% of our overall precipitation, summer precipitation in one day. That's basically where we say we have one very, very wet month, followed by a couple very dry months, followed by wet months. And what that does is it doesn't really create drought impacts to water supply. So Champaign or Decatur, throughout Decatur's a little special, but Champaign or Bloomington Normal or Peoria or Chicago's water supply isn't going to be affected by a drought that only occurs for 1 or 2 months. But we do see impacts to agriculture, depending on the timing of the drought, and ecosystems, natural ecosystems, including flora and fauna. And so that this kind of change in the characteristics of drought is something that is projected to continue into the future, where instead of getting these long, protracted, kind of slowly evolving droughts that we think of the 1930s, where they last many, many years, we get these short but very intense droughts that have different sorts of impacts. I want to just show this here. This is kind of new results here, if you will. This is on the left-hand side. This is showing monthly precipitation departure from normal for this year in Mount Pulaski there in Logan County. And what this is showing is that the first 5 months of the year in Mount Pulaski were wetter than normal, actually quite a bit wetter than normal. And the last 5 months that we've had, June through October, have actually been drier than normal, which is pretty incredible considering we have 5 consecutive wetter, 5 consecutive drier. Now, again, hey, you average this out, Mount Pulaski is actually still a couple of inches above normal for this time of year for the entire calendar year. But of course, if you're a farmer, producer, you're thinking about natural resource manager in Logan County, having 5 consecutive drier than normal months, especially when those months are the months when we have the highest evaporative demand, June, July, August, that does create an issue. Okay, so I'm going to move now into talking about projected changes. So this is projections into the future. One thing I'm going to discuss very briefly are these representative concentration pathways. So what we do in climate science is to really evaluate projections from Earth system models or global climate models. Consistently, we take a bunch of models and run them under using the same sorts of assumptions for changes in greenhouse gas emissions. So we say, okay, under this assumption that greenhouse gas emissions increase from X to Y over the next 100 years, or increase from X to Y and then slowly decrease, or decrease from X to Y, here's what the models think our climate change impacts are going to have. And overall, usually what this means is that we can, again, compare differences between models pretty consistently, but also say, okay, if we curb carbon dioxide emissions or greenhouse gas emissions by this year, we can have this lesser impact or lesser magnitude impact. So overall, a lot of folks will talk about the higher emissions scenario or pathway and the lower emissions scenario. RCP 8.5, that's the radiative forcing, that's the higher emission scenario. RCP 4.5 is the lower emission scenario overall. So when I talk about projected changes in climate, I use those two scenarios to give you an idea for how sensitive that climate change is to future greenhouse gas emissions. Okay, so that's what we have here. What I'm showing here are plots of temperature, projected change in temperature to the end of the century, essentially to 2100. These plots are shown in the top are northern Illinois, the middle is central Illinois, the bottom is southern Illinois. On the middle plots here on the left-hand side, those are showing projected changes in average annual average mean temperature. So what you can see a couple of things here. Overall, the models pretty consistently project continued increases in annual average temperature in all 3 regions of Illinois. However, you see that the red area, which is the higher emission scenario, if we continue emitting carbon dioxide emissions or greenhouse gas emissions at historical rates, that is somewhat split from the lower emission scenario. What this is suggesting is that the magnitude of temperature change between now and the end of the century is very sensitive to the emissions, the amount of greenhouse gas emissions between now and the end of the century. So overall, fewer emissions means overall less warming and lower magnitude impacts from that warming. On the right-hand side, these plots are showing the same thing, only instead of annual mean temperature, it's the annual number of days with a maximum temperature over 95 degrees. So we think about those as very hot days. And so what we can see here is kind of the same thing, a projected increase overall in northern, central, and southern Illinois in those very hot days, but the magnitude of that increase varies tremendously with the scenario itself. So again, we can say, if we decrease carbon dioxide emissions if we curb them essentially, then we see overall fewer heat waves. And again, this is really good when communicating, especially to policymakers, to say, some of these impacts are cooked in, so to speak, to use a terrible pun, but change in the way of reduced emissions can actually result in fewer impacts, or at least lesser magnitude impacts, especially as temperature is related. When we think about precipitation, it's a little bit different. What I'm showing here are projections of precipitation on the left-hand side by mid-century, so 30-year period that splits 2050, and on the right-hand side, late century, so you think about 2080 or so. And the top plots, the top maps are lower emission scenario, the bottom maps are that higher emission scenario. So overall, the blues, the greens across the state, these are showing projections of continued increases in precipitation under all emission scenarios. So overall, the projected changes are largest. The wetting is largest in Northern Illinois relative to Southern Illinois, but overall, the state is expected to continue to get wetter. When we break that down by season, we actually see something very interesting. So winter, spring, summer, fall. Winter and spring are showing the disproportionate largest increases in precipitation, the projections, whereas fall stays pretty much the same, and summer actually shows a projected slight decrease in summer precipitation. So, and this is pretty consistent with projections, with climate model projections. What they're suggesting is that precipitation on a whole as an entire year is projected to continue to increase, but the seasonality of that is going to change. We're going to see continued increases in winter and spring precipitation with decreases in summer precipitation. Now, if you're thinking about impacts related to that, we could, it does bring about this idea of flooding in the spring followed by drought in the summer. I will caution, though, that first and foremost, the projected changes in summer precipitation are very small, 0 to 5% for the entire, for most of the state. And when we think about those small projected changes, we really need to consider that in the context of the error or uncertainty in these model projections, which is much higher for summer precipitation than for winter or spring. So overall, when I'm giving these sort of talk to policymakers, folks, especially farmers, who are concerned about projections of summer drought, I do caution them a bit to say that models do have a difficult time picking up summer precipitation. So there is still quite a bit of uncertainty surrounding these projected decreases in summer precipitation. It's very likely we'll continue to see increases in winter and spring precipitation. The summer, it's a little bit less. And that's particularly the case when you contrast, projected summer drying with what we've seen over the last 100 years, which is actually summer has gotten wetter to a larger degree than any other season in Illinois. This is kind of showing the same thing with Champaign County. We see overall the projections are showing a decrease in precipitation from current in June, August, and September and October, which of course can increase the risk of moisture stress in summer and fall. We also see continued projections and continued increases in extreme precipitation. So it's in this case, the number of days where we have 2 inches or more in a single day. The differences in emission scenarios here for extreme precipitation are actually not as large as temperature. So what this is suggesting is that unlike temperature impacts, changes in precipitation are not necessarily as sensitive to the emission scenario, meaning that if we decrease carbon dioxide emissions, it doesn't necessarily result in the large change or decrease in precipitation related impacts as it does with temperature related impacts. Okay, so this is where I transition away from my sweet spot of climate and get into your all sweet spot with birds. Fortunately, the Audubon Society has helped me out with this awesome report that they put out in 2019. So what this is showing is the number of species of birds in Illinois differentiated by their vulnerability to climate change. And this is vulnerability to climate change defined broadly, not just changes in temperature or precipitation, but also changes in the distribution of food sources, of biomes, changes, things like that. So overall, what this is suggesting is that there are a large number of bird species that are at either moderate or high vulnerability or risk due to climate change, projected climate change here in Illinois. And a lot of that goes to the changes in temperature and the shift in ecosystems and biomes here in the state, as well as the distribution of food sources. You can see that summer, we have a larger impact or larger vulnerability of species in the summer than changes in the winter. And a lot of that, again, is due to those projections of continued summer warming and increases in extreme heat, increases in moisture stress, and of ecosystems and overall ecosystem failure. At the same time, this is a study by Reifelt et al. In 2012 showing these maps. On the left-hand side, this is our current biome distribution. And the green here throughout much of the state is our grassland, our prairie grassland. The kind of weird grayish color to the east is a temperate deciduous forest. On the right-hand side, we see the same map, only this is projections of the changes in biomes across North America by the year 2080. And what this is suggesting is that as we see temperatures continue to increase and moisture stress in the summertime increase because of either decreases in summer precipitation or increases in summer evaporative demand, it makes a more conducive environment for temperate deciduous forest, that the kind of biome that can deal with more rapid and more frequent disturbances from extreme heat and moisture stress than can grassland. And with that, combined with the succession that is pushing out oak species in our current forests in Illinois in favor of beech and maple, compounded by fragmentation, of course, with development and agriculture, that overall increases the disturbances. So what we see, what this report finds is that a lot of this vulnerability of bird species that I'm showing here are due to a number of things related to climate change directly. So increased summer temperature, decreased summer precipitation, but also as a result of those as an indirect impact, more fragmentation, increased disturbance. So a disturbance can be flooding of an ecosystem because of increased precipitation intensity, increased short-term dry spell or drought, increased extreme heat. And there's actually quite a bit of research out there suggesting that even though temperatures in winter have warmed considerably, we still see about the same frequency of cold snaps here in Illinois, where we get that very cold air that lasts for a very short period of time. And so those increased disturbance compounded by fragmentation and overall climate change result in an increased vulnerability of multiple bird species here in Illinois. Overall, the study found 29% of Illinois' bird species are vulnerable to climate change one way to another. They break it down again: urbanization, cropland expansion, that goes to, of course, habitat fragmentation, extreme spring heat. So I talked about increases in summer heat, but extreme spring heat is an issue as well as we continue to see those spring temperatures increase. And then fire weather. Fire weather is something that we think of as out west, but of course we came face to face with fire earlier last month when we had that really severe fire weather and a couple of field fires break out. That is also a concern, especially as if we increase summer temperatures and decrease summer precipitation, it makes for overall more dry fuel if we do get that fire weather in the summertime. Based on that study, the species most at risk: bobolink, red-headed woodpecker, field sparrow, brown thrasher, and wood thrush. Those are the ones at the very highest amount of vulnerability. Again, a lot of that due to a northward shift in habitat and the distribution. But again, the nice thing about studying these different pathways of climate change is that the study concluded by saying that reduced warming from 3 degrees Celsius by the end of the century to that 1.5 degrees Celsius that Paris Climate Agreement tried to target, that would more than halve the overall avian risk to climate change in Illinois. And so that is something that is important to take away from that report as well, that again, some of this is quote unquote baked in, but changes in emissions between now and the end of the century can still help mitigate or prevent some of these impacts. So lots of summary here. I've talked about all these points before, so I don't want to waste time rehashing them, but overall, we see, climate change does pose a significant impact to birds and ecosystems in Illinois. And it is something that, again, we know the cause of, and we can link to, the greenhouse gases and radiative forcing and warming from that. And you know, a lot of times I'll end these talks by saying, okay, here's all the problems. Now you all find the solutions. But in this case, again, I like to stress that, especially as it relates to impacts to birds and ecosystems, a lot of the impacts that we project by the end of the century can be prevented by decreases in overall greenhouse gas emissions between now and that time period. So thank you again for letting me speak tonight. And please, if you ever have any questions, want any data, you know, have other events that maybe you want to come hear me, or you want me to come and ramble at, I'd be happy to. Please feel free to reach out to me at any time. And just thank you again for letting me speak.
Awesome. Thank you so much. I, of course, have questions, but I will open up if anyone wants to actually join via audio and ask questions, you're welcome to. We just want to keep them as unoverlapping as possible, but you're also welcome to put a question in the chat and I can read that to Trent to answer. That is up to you. There we go. Okay, so now we're getting some positive comments. One of the questions I wanted, I mean, this, before everyone leaves too, this is a very good point to acknowledge that, you know, one of the biggest things we can do locally for climate change is, of course, limit habitat destruction, maintain conservation areas, and maintain them properly. And so, you know, one thing that has benefited recently is the Yes to Forest referendum, which is going to not only maintain some of the actual parks and recreation services that are offered through the Champaign County Forest Preserve District, but also the conservation and active management of these properties to make sure that they continue in the future as havens for these birds that travel through our migratory flyways. And I think the other thing that I've always noticed, you know, I'm from Eastern United States. I'm from the Northeast. New York lake effect is a huge thing where I am. And I've always found the climate here very interesting. And it was nice to see it in visual form, seeing that the summers are very dry, the spring and winter is very wet, you know, these weird patterns of drought and precipitation. But also, it seems like one thing I wanted to ask is, some of these weather systems that tend to come through the area seem to dissipate seemingly before our eyes before they get to Champaign. Does that have to do with like microtopography of the region? Does it have to do with the actual air currents that commonly come through the, you know, collide right near where we are? What is the main driver behind that strange phenomenon?
Yeah, so this year has, I've been preparing my talk to the agriculture community, because, you know, once harvest is done, then the talk begins. And so, you know, a lot of folks are wanting to know, especially in Central Illinois, you know, what was happening this year. This year, for most of Central Illinois, for most of the Central Belt, essentially I-72 just straight across the state, it's been very dry in the summer. And this year, what you're talking about is definitely the case. We saw where the position of the jet stream, which is the dominant driver of where systems are crossing, where these storm systems are moving across the US, the position of the jet stream was sometimes in Northern Illinois, sometimes it was pushing systems in Southern Illinois. And it just so happened that this year we had a lot of systems that were producing rain to the south of that I-72 corridor, to the north of the I-72 corridor. And it just seemed that area, you know, 30 or 40 miles splitting that interstate, were just missing out on rain. And there is no phenomenon behind that. It just, in this case, it was just the way it fell. You know, and so that was an interesting phenomenon, honestly, this year. And if you move closer to Decatur and Lincoln, they're even drier than we are here. But overall, yeah, there's nothing, there's really nothing kind of permanent to say like, this is something that would cause a dissipation of a system. This year, it just so happened to be that consistently pressure patterns were making it so that this area stayed dry while areas somewhat surrounding got the rain that they needed.
Interesting. Okay. Yeah, because being from an area with lake effect, like I said, I'm kind of used to not being able to predict the weather. You know, it's similar to like the mountains where it kind of just changes depending on the weather or the temperature or the humidity of that day or whatever. And I just kind of gave up on trying to look at the weather report this year.
Yeah, well, and summer is difficult. You know, summer weather is far more difficult to forecast.
Yeah.
Just because we have the smaller scale drivers that can change really rapidly. Yeah, so
Sure.
then overall the winter patterns. But yeah, we actually did get in Champaign, we did get in March, it was a late March snowfall event. We did actually get lake effect snow.
Yeah.
Amazingly. We had just a band of snow that came down from Lake Michigan. It just so happens. So that happens every once
Love
in a
it.
while.
I
Certainly not.
remember it specifically. I went out to enjoy it because it was enough snow that I could actually, I have brought snowshoes with me and I've never been able to use them. So
Yeah, yeah.
cool. Well, we have a question here from Barbara Schleicher that says, is there a correlation between a wetter Midwest and a very dry Western United States?
Yeah, that's a really good question. On a longer time scale, there's not any sort of combination driver, like one thing that causes it to be very, very dry or drying in the West over the last century and wetting in the East necessarily, or the Midwest. We can get a certain pattern on a short time scale that can establish primarily what it is. If you think about the geography of the US, we get a ridge in the jet stream. I'm going to try to kind of bend my hand here. A ridge in the jet stream over the Western US that often associates with a trough in the Eastern US. So the jet stream, it's waving in a kind of a wave-like pattern. The ridge generally means it's going to suppress any sort of precipitation event, and it makes it very dry in the West. The trough, the dynamics are going to create low pressure systems that can create precipitation. And so in that way, if that system, if that ridge trough can establish and it persists over a number of weeks to, in some cases, months, you can get a situation where you have a very dry Western US and a very wet Eastern or Midwest US, and that's caused by the same phenomenon. On the flip side, in the summertime, if we get a big ridge in a very, very dry West and that ridge breaks down, that dryness and that heat will spread our way. And that's what happened this year. We had in kind of early to mid-August, it got very dry and very warm. And that was those ridge that had been baking the Western US for a month, it broke down, and that heat just spread out and made it very dry here as well. So things are interconnected for sure. So that is one. But certainly, the drying trends that we've seen in the West, we've seen the exact opposite here. The Midwest has gotten wetter overall.
Thank you. Okay, so Greg asked, how different do scenarios in other United States regions look? So in other areas of the US, is it similar? Is it different?
In the Northeast US, it's pretty similar here to the Midwest, wetter and warmer overall. The Southeast US is, they're a bit of an enigma. You may or may not have heard of the warming hole in the Southeast, where temperatures haven't warmed as much as other places. That has actually since kind of broken down a little bit. They have seen increases in temperature, and projections indicate that the Southeast may get drier overall. Although trends in the Southeast and even breaking into Texas have actually been trending slightly on the wet side. The Western US has gotten slightly drier. Things move slower in the Western US. So they have these kind of multi-decadal, there's this pronounced multi-decadal variability in the Western US that can drive these kind of multi-year, or in some cases multi-decade dry spells or drought events. Mega droughts, I think, is what some of the papers call them in places like California and Arizona. And so they can be in this kind of persistent drought for a number of years. And so trends there are can be a little bit more difficult to assess, but overall they're seeing warmer temperatures and overall drier conditions. So it does vary as far as other regions in the US. You know, for us here in the Midwest, you know, I think that the biggest impact so far from climate change has really been the increase in precipitation, the flooding from that. You know, I talked about increases in drought and those short dry spells, and that has had an impact, but those are mostly relegated to agriculture. But for the flooding events and the increased precipitation intensity, that's, I think, really been our major impact.
Great, thank you. Okay, we have a couple more questions. Kathy asked, you showed a map depicting decadal temperature changes in Illinois. Temperature increases in East Central Illinois were higher than elsewhere in the state. Are these regional differences statistically significant and robust?
That's a really good question. The differences between Eastern, that county map, I think is what you're referring to, Kathy, and that the differences between counties I haven't assessed for statistical significance. The trends themselves within a county I have, and they are statistically significant. But yeah, you see kind of a warming between central Illinois, essentially between Peoria and Danville, including this area. I don't know. I certainly can't explain why it's warmed here at a larger rate than in other places. I'd want to assess those trends for statistical significance, you know, the differences before I would say that they're due to any sort of large scale driver. But that is a really good question. That kind of warming, especially in that area, is actually that area sticks out in almost every season. So it seems to me that given that it's probably just a figment of the data, and maybe not necessarily some sort of driver that's something that's going on here in East Central versus West Central Illinois, but I don't know enough about that yet to say for sure. That's a really good question.
Yeah, and if anyone is, I know most of this I see on Twitter. Trent is very active on Twitter and shares maps and graphics and new research all the time. So I'm not sure if you have another place that you cross-post that material, but for anyone who wants to keep up with what he's doing, it's constantly updating new information about whatever you're
Sometimes
researching.
too much. These days, it's easy to stay on Twitter instead of doing work, I think.
So is there anywhere else? Do you have that also up on the website as well, the climatology?
Some of the things, yeah. So the State Climate website, the State Climatologist website has a lot of that material. I do monthly updates, which are also, the blogs are posted on the State Climatologist website. Just to say, okay, was last month's weather and climate, just a little bit of a summary. I usually like to throw in some interesting statistics. For example, if anybody's from the Belleville area in Southwest Illinois, even though it's been dry here, that place at Belleville is only about 4 inches away from its record wettest year, which was 2008. So, and climatology tells us that they will reach that if they have a normal November and December. So interesting little things like that. So yeah, that is on the website. And then if you are on Twitter, you know, feel free to follow me. I do try to split time between the website and Twitter, but it is pretty easy to post things on Twitter as well.
Definitely. Okay, Anne would like to know, do you expect there to be a change in tornadoes and severe thunderstorms?
That's a really good question. There's a great graphic. I need to just have it in my back pocket all the time that NOAA put out that basically shows like how certain we can be that climate change is going to affect something. So for heat waves, we can be fairly certain, strongly certain. For severe thunderstorms, it's very difficult. Now, theoretically, more heat, more humidity, more energy, we should see more severe, more frequent thunderstorms. But because severe thunderstorms are complex mechanisms, not just requiring the temperature to get very high, you know, it requires a lot more. You know, research into how climate change affects severe thunderstorms is unclear. Also, our models, you know, and I show you those projections the actual physics of the atmosphere are being projected or being modeled at maybe a 100-kilometer resolution, spatial resolution, 80 miles or so. So what that means is that coarse resolution can't pick up on severe thunderstorms very well. So we don't really have a lot of certainty about, okay, we're going to see more or fewer severe thunderstorms. As far as tornadoes are concerned, projections kind of the same way. Tornadoes are even more difficult to project, but we have seen a shift, an eastward shift in tornado alley, quote unquote, where we are seeing an eastward shift in the area of the U.S. that receives the maximum amount of annual tornado activity. And that kind of shift, the area that has over the last 10, 15 years been the most active as far as tornado activity goes from kind of the Texarkana area, Louisiana, Arkansas, Texas, meeting up into Southern Illinois. And so we have seen the frequency of tornadoes, especially in the southern half of the state, increase. And so that is something that's interesting. However, the increase has been almost entirely in EF0 and EF1 tornadoes, so the very small tornadoes, but still something interesting. And it will be interesting once models get even finer resolution, better at the model physics, if they can start picking up, supercells are the things that are generating those tornadoes. It'll be really interesting.
Yeah, and if I've learned anything about models through my short academic career so far, it's that there's many, many moving parts, and the smaller spatial scale you get, the more difficult it is sometimes. So,
yeah.
Okay, so we have a couple more questions from Kathy that are good questions. Is anyone at the Water Survey running regional climate models? And are the soil moisture data consistent with temperature data? i.e., are soil moisture levels being stressed in East Central Illinois?
Yeah, good question. So there are folks at the Water Survey who are running regional climate models. I'm an observationalist myself, so a lot of my work deals with observations, but I collaborate with folks who are more modelers. And yeah, they'll strap a regional climate model onto a GCM or couple them together to get at better, more fine resolution modeling. And that's especially important for hydrologic modeling for smaller watersheds. So that is going on at the Water Survey. As far as the soil moisture data, soil moisture, we don't have soil moisture data for nearly as long, observations for nearly as long as temperature or precipitation, unfortunately. What I have seen with soil moisture data is that we've actually seen an overall increase in soil moisture, despite the decrease in temperature or the increase in temperature. Although we have these short time periods where soil moisture may be stressed, like this summer or right now, for example, was pretty dry, the long-term trend is still small, but still significant increase in overall soil moisture in Illinois. And that's mainly from that precipitation. Now, the projections from climate models show that, as temperatures continue to warm and precipitation gets more seasonally variable, that soils will actually begin to be stressed more often, especially in the warm season. And that goes back to that change in ecosystem health and the kind of biomes, the kind of ecosystems that can thrive or not thrive in an area that is climatologically not moisture stressed, but that becomes moisture stressed more often. And that's kind of where the projections are suggesting we're going.
Yeah, I would assume it partially has to do with the type of, depth to the water table and type of soil we have too. I mean, we have these deep, rich soils as opposed to areas where there's maybe, mountainous regions where there's a very thin layer of topsoil that may not be able to hold that moisture. So cool, very interesting. Well, if anyone else has any questions, feel free to reach out to Trent at another time via Twitter or his email, which I will send out a follow-up link when this is posted to YouTube in case anyone wants to revisit any of the graphics that were showed in this presentation. And I can also send out contact information if that's something people are interested in. So feel free to reach out if you have any questions for me. And thank you for talking to us this evening. It was wonderful.
Yeah, thank you for having me. It was really a pleasure. So take care, and everybody have a fun and safe weekend then.
Thank you. Yeah, you too. Everyone stay positive and remember, what do they say? Think global, act local. So if you are feeling overwhelmed by anything this week, just reach out to your community and see what you can do here. And we can definitely give you things to do if you're in need of some local action. So just get in touch. Cool. Thank you, everybody. I hope you have a great week. Thank you, Trent. We really appreciate it.
Thank you again. Take care.
All right. Thanks. Bye.